Welcome to this lesson on mixing in microchannels. Today we're going to explore why mixing becomes incredibly difficult at microscopic scales, and the clever engineering solutions that overcome this challenge. Before we dive into the physics, let's ask ourselves, why should we care about mixing in tiny channels? Microfluidic devices are revolutionizing medicine and chemistry. Lab-on-chip devices can analyze blood samples with just a few microliters. Drug synthesis at microscale offers precise control. Chemical sensors need rapid mixing to detect substances quickly. Here's a typical microchannel. It's about 100 micrometers wide, roughly the thickness of a human hair. Two fluids enter from the left. In a large pipe, turbulence would mix them rapidly. But in microchannels, something very different happens. To understand why mixing is difficult, we need to introduce the Reynolds number. This dimensionless parameter tells us whether flow is turbulent or laminar. The Reynolds number equals rho UL divided by mu. Rho is fluid density, U is velocity, L is characteristic length, and mu is dynamic viscosity. When Reynolds number exceeds about 2,300, flow becomes turbulent. Chaotic eddies and vortices naturally mix fluids together rapidly. When Reynolds number is below 2,300, flow is laminar. Fluid moves in smooth, parallel layers with no cross-stream mixing except by molecular diffusion. Let's calculate the Reynolds number for a typical microchannel to see what we're dealing with. Consider water flowing through a 100 micrometer wide channel at 1 millimeter per second, which is a typical microfluidic velocity. Water density is 1,000 kilograms per cubic meter. Water viscosity is 0.001 Pascal seconds. The characteristic length is 100 micrometers, which equals 10 to the minus 4 meters. Velocity is 1 millimeter per second, or 0.001 meters per second. Plugging in these values, 1,000 times 0.001 times 10 to the minus 4, all divided by 0.001, gives us a Reynolds number of 0.1. A Reynolds number of 0.1 is far below the turbulent threshold. The flow is completely laminar. There are no turbulent eddies whatsoever to help with mixing. In laminar flow, molecular diffusion becomes the only mixing mechanism. Let's explore how long diffusion takes. The diffusion time scales as L squared divided by D, where L is the distance molecules must travel and D is the diffusion coefficient. For typical small molecules diffusing in water, the diffusion coefficient is about 10 to the minus 9 square meters per second. Let's calculate how long it takes for molecules to diffuse across our 100 micrometer channel. 10 to the minus 4 squared equals 10 to the minus 8. Divided by 10 to the minus 9 gives us 10 seconds. It takes 10 seconds for molecules to diffuse across just 100 micrometers. This seems short, but consider the flow velocity. Here's an important question. While molecules are slowly diffusing sideways, how far downstream does the fluid carry them? Distance equals velocity times time. 0.001 meters per second times 10 seconds equals 0.01 meters, which is 1 centimeter. You would need a channel at least 1 centimeter long just to get basic mixing. For microfluidic chips, this is extremely long. We want compact devices. This diagram shows the problem. Blue and red fluids enter side by side. They flow as parallel streams for a very long distance. Only at the end, after 1 centimeter, do they become reasonably mixed. Let's develop some intuition. Why is diffusion so painfully slow? Think of a molecule as a drunk person taking random steps. Each step goes in a random direction. To travel a net distance L, you don't take L steps, you take many more. The net distance L scales as the square root of n times the step size L. Rearranging, the number of steps needed scales as L over L quantity squared. This square relationship means doubling the distance requires 4 times as many molecular collisions. This is why diffusion time scales as L squared. Can we somehow make diffusion faster? Unfortunately, not really. The diffusion coefficient D depends on molecular size, temperature, and viscosity. For a given fluid at a given temperature, it's essentially fixed. The only practical solution is to reduce the distance L that molecules need to travel. If we can break up the fluid into thinner layers, diffusion across each layer is faster. This brings us to the brilliant solutions engineers have developed. They use fluid mechanics to stretch, fold, and rearrange fluid streams, dramatically reducing diffusion distances. Chaotic advection uses specially designed flow patterns to exponentially stretch fluid interfaces, creating thin layers that mix quickly by diffusion. Think of kneading bread dough. You stretch it, fold it over, stretch it again. Each fold doubles the number of layers and halves the thickness. After n folds, you have 2 to the n layers. Here's the concept visually. Start with 2 fluids side by side. Stretching elongates the interface between them. After n stretch and fold operations, you have 2 to the n layers. The layer thickness becomes the initial thickness divided by 2 to the n. The diffusion time decreases dramatically, as L naught squared over 4 to the n times d. After just 5 folds, you have 32 layers, and the diffusion time is reduced by a factor of 1024. This is exponentially faster mixing. The question is, how do we physically create this stretch and fold motion in a microchannel where flow is laminar? We exploit 3-dimensional flow patterns. By carefully designing the channel geometry, we can make fluid particles follow complex twisting paths that naturally stretch and fold the fluid. One of the most elegant solutions is the herringbone micromixer, invented by Struck and colleagues in 2002. Herringbone mixers have asymmetric grooves patterned on the channel floor. These V-shaped grooves are angled relative to the flow direction. You might ask, how can simple grooves on the floor create complex 3-dimensional flow? The angled grooves force fluid to flow diagonally. Fluid near the floor follows the groove direction. This creates helical rolling motions perpendicular to the main flow. Looking at the channel cross-section, the herringbone grooves generate counter-rotating vortices. Fluid circulates up on one side, across the top, down on the other side, and back along the bottom. These vortices continuously stretch and fold the interface between the 2 fluids. Blue and red fluids are wrapped around each other in increasingly complex patterns. Let's estimate how much shorter the channel can be with herringbone structures. Each herringbone pattern, spanning maybe 500 micrometers, creates roughly 1 stretch and fold cycle. 5 cycles takes 5 times 500 micrometers, which equals 2.5 millimeters. With herringbone structures, we achieve good mixing in just 2.5 millimeters. Compare this to 10 millimeters for purely diffusive mixing. That's a 4-fold reduction in channel length. Another approach is the serpentine or zigzag channel. This uses sharp turns to create secondary flows. A serpentine channel has sharp 180-degree bends. The flow path zigzags back and forth. When fluid flows around a curve, centrifugal effects create secondary flows called Dean vortices. The Dean number equals the Reynolds number times the square root of the channel radius over the curve radius. These Dean vortices are similar to the vortices in herringbone mixers. Fluid spirals as it goes around each bend, creating transverse mixing. Each turn of the serpentine channel contributes additional stretching and folding of the fluid interface. Multiple bends accumulate this effect. Here's the cross-sectional view in a curved channel. The Dean vortex creates a circular flow pattern that rolls the fluid streams around each other. Let's compare purely diffusive mixing, herringbone structures, and serpentine channels. Pure diffusion requires about 10 millimeters for our example. The advantage is the channel geometry is extremely simple, just a straight tube. Herringbone mixers reduce mixing length to 2 to 3 millimeters. However, they require precise microfabrication to create the groove patterns. Serpentine channels achieve mixing in 3 to 5 millimeters. They're easier to fabricate than herringbone structures but take more space on the chip due to the turns. Let's dig deeper into the physics. Why do these methods work so well? Even though the flow is laminar, advection, the transport of material by fluid motion, is still much faster than diffusion. The Péclet number equals UL over D. This dimensionless number compares advection rate to diffusion rate. Let's calculate the Péclet number for our 100 micrometer channel. 0.001 times 10 to the minus 4 divided by 10 to the minus 9 equals 100. A Péclet number of 100 means that advective transport is 100 times faster than diffusive transport. The brilliant strategy is to use the fast advection to rearrange the fluids into thin interleaved layers. Then, the slow diffusion only needs to work across tiny distances to complete the mixing. You might wonder, if chaotic advection is so effective, Why don't we use it in large industrial pipes? In large pipes at typical flow rates, the Reynolds number is high, often thousands or tens of thousands. The flow is naturally turbulent, which provides excellent mixing without any special geometry. You can think of turbulence as nature's own chaotic advection. Random eddies at all size scales stretch and fold the fluid extremely efficiently. Microchannels have such low Reynolds numbers that turbulence cannot exist, so we must engineer artificial chaotic advection using channel geometry. Let's do a more rigorous quantitative comparison of mixing efficiency. We can quantify mixing quality by measuring the standard deviation of concentration across the channel. Perfect mixing means uniform concentration everywhere. With pure diffusion, the mixing quality improves as the square root of time. This is slow, following the square root scaling of diffusion. With chaotic advection, mixing quality improves exponentially with distance downstream. Each fold doubles the number of layers, leading to exponential improvement. The concentration standard deviation sigma decreases as e to the minus x over lambda, where lambda is the characteristic mixing length. When designing a real microfluidic mixer, engineers must consider several practical factors. More complex geometries create higher pressure drops. Serpentine channels with sharp turns and herringbone grooves both increase flow resistance. This requires more pumping power. Herringbone structures require multi-step lithography and etching. This increases fabrication cost and limits materials. Serpentine channels are easier to make. Some designs work well only at specific flow rates. The optimal design should provide good mixing over a range of operating conditions. For biological applications, sharp corners and high shear rates can damage cells. Gentler mixing strategies may be needed. Researchers have extensively studied how to optimize herringbone mixer geometry. The groove depth, angle relative to flow, spacing between grooves, and degree of asymmetry all affect mixing efficiency. Deeper grooves generate stronger secondary flows and better mixing, but they also create more flow resistance. Studies show the optimal herringbone angle is typically around 45 degrees relative to the flow direction. This balances vortex strength and path length. Alternating the herringbone direction, left-angled, then right-angled, creates even more complex flow patterns and improves mixing further. Let's consider a real application where microchannel mixing is critical. In DNA detection assays, fluorescently labeled DNA probes must mix with the sample rapidly. The probes bind to complementary target sequences. Without efficient mixing, the assay might take 5 to 10 minutes. With a herringbone mixer, binding can occur in 10 to 20 seconds as the sample flows through. Fast mixing enables real-time monitoring of chemical reactions and biological processes, which is impossible with slow diffusive mixing. Modern mixer design relies heavily on computational fluid dynamics simulations. Engineers solve the Navier-Stokes equations to compute the three-dimensional velocity field throughout the complex channel geometry. They track thousands of tracer particles to visualize how fluid elements are stretched and folded. This reveals the chaotic mixing patterns. Finally, they solve the Advection diffusion equation to predict the actual concentration distribution and quantify mixing quality. These simulations allow testing many designs virtually before committing to expensive microfabrication. This dramatically accelerates the design process. Let's recap the key dimensionless numbers that govern mixing in microchannels. Reynolds number, rho UL over mu, tells us if flow is laminar or turbulent. Péclet number, UL over D, compares advection to diffusion. Dean number, Reynolds number times square root of channel radius over curve radius, characterizes secondary flows in curved channels. These dimensionless numbers encapsulate the essential physics. By calculating them, engineers can predict mixing behavior without detailed simulations. Let's summarize the key concepts we've covered in this lesson. Mixing in microchannels is fundamentally difficult because the Reynolds number is very low, typically much less than 1. There is no turbulence to aid mixing. Molecular diffusion alone is extremely slow, with mixing timescaling as L squared over D. This leads to impractically long mixing lengths. Chaotic advection exploits carefully designed channel geometries to create three-dimensional flow patterns that stretch and fold the fluid interface. Herringbone mixers use asymmetric grooves to generate counter-rotating vortices that continuously roll the fluids around each other. Serpentine channels exploit Dean vortices that form naturally when fluid flows around sharp bends. Both approaches reduce the required mixing length by factors of 3 to 5 compared to pure diffusion, enabling compact microfluidic devices. The underlying strategy is to use fast advective transport to create thin interleaved layers, then let slow diffusion complete mixing over short distances. Mixing in microchannels beautifully illustrates how physical constraints at different scales demand different engineering solutions. Understanding how things scale, like the square relationship of diffusion time with distance, guides us toward creative solutions. Simple geometric modifications, like grooves or curves, can generate surprisingly complex and useful flow physics. Microfluidics represents a frontier where fundamental physics meets practical engineering at scales where our everyday intuition often fails us. Thank you for joining this deep dive into mixing in microchannels.